All right, so good evening, everyone. My name is Chester Anajan Nixon, holding matrix number 82483, and I'm representing Group 17, one of the presenter for the AMS Group project. So, without further ado, let us go to the next agenda or the next slide of this slides. All right, so here is a brief explanation on the company that we are going to study. All right, so Company Z has been operating successfully in the domestic market for over 20 years, basically. But however, the company is now expanding into the Middle East export market, where it expands the business itself to Qatar this year. So, where it will have a higher competitor and also with a different quality, consistency, and regulatory standards will be more stringent. All right, so this transition methods highlights the need to move beyond conventional production methods and adopt and advance manufacturing systems to remain competitive. All right, so the project focuses on transitioning Company Z from domestic focused manufacturing to an export oriented production system. It emphasizes the integration of automation, quality control, and production planning to ensure stable operations, high throughput, and scalability. The proposed system is designed as a strategic solution for management approval to support long term export growth. All right, so, despite its success domestically, the current manufacturing system that is still in use by Company Z was not designed for large-scale export production. Product quality can be inconsistent, and without a structured evaluation, there's a high risk of selecting an inappropriate automation architecture, which could lead to high costs and poor system performance. All right. In addition, the existing factory layout results in an inefficient material flow, increasing handling time and contamination risk. There is also no structured application of group technology, cellular manufacturing, or flexible manufacturing system concepts. These limitations reduce production efficiency and make it difficult to meet export market requirements. All right, so based on these problems, the objectives of this project are to design an export ready manufacturing system for cake production, apply group technology, cellular manufacturing, and FMS concepts, and develop a suitable automation and quality monitoring strategy. In addition, the project evaluates the technical feasibility and economic justification of the proposed system. All right, from the slides, it shows that automation has become increasingly important in the bakery and confectionery industry, especially as manufacturers move towards large scale and export oriented production. Automation helps ensure consistency in ingredient dosing, mixing, baking, and packaging processes. In food manufacturing, human handling is a major source of variability and contamination risk. By reducing manual intervention, automated systems improve hygiene and repeatability. This is particularly critical for cake manufacturing, where small variations in mixing or baking conditions can significantly affect product quality. Therefore, automation is widely recognized in the literature as a key enabler for consistent quality, higher throughput, and compliance with international food safety standards. Right, for meanwhile, in the slides over here, it highlights the cake manufacturing is highly sensitive to process parameters such as mixing time, mixing speed, baking temperature, and baking duration. Even minor deviations in these parameters can result in defects such as uneven texture, incorrect weight, or poor appearance. As a result, modern food manufacturing systems emphasize process control and real-time monitoring rather than relying solely on final inspection. Preventive quality control allows manufacturers to detect deviations early and correct them before defects occur. It shows that this shift from inspection-based to prevention-based quality control it leads to lower scrap rates, improved consistency, and also better compliance with supermarket and export requirement. Now, here is our manufacturing layout. Okay, so I will explain why there are three manufacturing lines that are involved here. Basically, in these manufacturing lines, we are going to mass produce our cake. And with the meaning of mass produce, this cake might will be made into batches in the near future. But to speeden up um, the cake making, we will do three cells, in which each of the cells here contain a raw material storage where all of the raw material will be kept, and excuse me, and it will move to the weighing and batching, and from it will move to mixing and depositing, and it will move to the baking and cooling, and second last would be the packaging and inspection, and last but not least would be the shipping area. Right. So Qatar's food sectors are relying heavily on imported food due to limited agricultural capacity. This has created strong demand for packaged and shelf food products, including bakery items in supermarkets and even hypermarkets. At the same time, Qatar enforces strict food safety labeling and halal certification requirements. These regulatory conditions place additional pressure on manufacturers to ensure traceability, consistent quality, and hygiene production practices. As a result, manufacturing systems designed for the Qatar market must consider not only production efficiency but also regulatory compliance and quality assurance.
Hello everyone, I am Nicolio with matrix number 82665 and I am the facility engineer for this project. I am presenting our factory automation strategy and financial justification. We are not just building a factory, we are engineering an export-grade manufacturing ecosystem. This proposal outlines how we will transition Company Z from small-scale production to a high-volume automated facility capable of meeting strict international standards. Let's start with the bottom line. Our mandate is clear, where Company Z must evolve to export to the Middle East. To achieve this, we cannot rely on manual processes. Our strategy relies on a hybrid distributed control system, or known as DCS. This balances the reliability of local machines with the centralized traceability required for food safety. The financial outlook is positive, where the total capex is 6.76 million ringgit and the ROI payback period is 2.7 years. My verdict is that we must proceed with the full automation to secure this market expansion. To build this facility, we focus on 5 core engineering objectives to ensure consistency and compliance. First, to support high-volume export-oriented cake production with consistent quality and minimal variability. Next, to integrate manufacturing operation, quality monitoring and data management into a single coherent system. The third one is to minimize manual handling and human error in compliance with food safety and hygiene standards. Next, to provide flexibility of product variants and future capability expansion. And lastly, to ensure cost-effective operation over the life cycle of the facility. Let's look at the control architecture. We selected a hybrid DCS model. We call this the Goldilocks choice because it solves two major engineering risks. First is avoid single point failure. Unlike purely centralized system where a server crash stops the factory, our local machine at level 1 maintain fault tolerance. A fault in line 1 does not in line 2. Next, avoid data silo. Unlike a decentralized system, we still feed data up to central SCADA in level 2 and enterprise integration at level 3 for global visibilities. This gives us the best for both worlds, which are operational resilience and compliance reporting. Exporting to the Middle East requires rigorous proof of process consistency. Manual logging is prone to human error and simply won't pass an audit. Our solution is a digital twin interface linked to our SCADA system. As you can see on the screen, the system automatically logs critical process parameters, CCPS, like temperature, mix time, and viscosity for every single batch. This converts a massive regulatory burden into automated real-time reporting. Moving to the physical layout, we have implemented cellular manufacturing with unidirectional flow. First, group technology. We use dedicated product families in linear cell to eliminate backtracking. Next, hygiene control. Crucially, raw ingredient which place is on the left never cross paths with cooked product which is on the right. Cellular independence. As shown by the dotted line, maintenance on line 1 does not affect the operational of line 2 to ensure uptime. To further reduce contamination, we have zoned the facility into three, which are red, blue, and gray. Red for raw materials, blue for high care or production, and gray for support. We are minimizing human intervention through three keys technology. First is AGV flat for just-in-time ingredient delivery in the red zone. Next is centralized conveyance, linking baking to packaging without human touch. And lastly, robotic packaging, using high-speed Delta robot into the blue zone. This automated material handling reduces both contamination risk and physical strain on the worker. Here is the breakdown for the 6.76 million ringgit investment. Category 1, which is machinery, which costs 5 million ringgit. This is the engine for our revenue. It includes 1.65 million ringgit for gas-fired industrial tunnel oven and 1.2 million ringgit for robotic packaging cell. Category 2, infrastructure, which costs 1.4 million ringgit. This covers hygiene upgrade like HVAC and flooring, which costs 800,000 ringgit, and our SCADA system server 450,000 ringgit. Category 3, logistic. This includes our AGV flat and our QC lab equipment. We are investing heavily in production assets, which are 74% of the budget to ensure the throughput. Finally, the financial justification. Our project profit increase is 2.5 million per year, driven entirely by the new export volume, while our annual OPEX for energy, labor and maintenance sits at 1.34 million ringgit. The slope for our cumulative net profits allow us to break even in approximately 2.7 years. So in conclusion, the efficiency gains and unlock export capability make this system financially viable within a standard 3 years investment horizon. We recommend immediate approval to proceed. That's all from me. Thank you.
Good day. Chapter 4 establishes the strategic bedrock for Company Z's transition to fully automated cake production. In a globalized market, maintaining consistency and safety is the only viable path to securing the regulatory approvals required for export. We are moving away from reactive, manual inspection toward a proactive Quality 4.0 framework. By merging traditional methodologies with digital tools like wireless sensors and advanced analytics, we create a continuous feedback loop that ensures both safety and long term competitive positioning. Next, our monitoring system functions as the central nervous system of the bakery. It is organized into three-tiered hierarchy, where level 1, which is the equipment, its sensors track mechanical integrity, such as motor, torque, and speed. For level 2, which is the process, we use statistical process control to assess overall line stability. And for the last one, level 3, which is the plant-wide, we monitor strategic key performance indicators like overall equipment effectiveness and energy efficiency. This architecture ensures that real-time factory data is converted into valuable business intelligence via enterprise resource planning and quality management system integration. Moving on, to eliminate material waste, we utilize online monitoring to track parameters like batter consistency and oven humidity in real time. We measure our process capability quantitatively, targeting a process capability index of more than or equal to 1.33 to ensure we meet design specifications. While online telemetry provides the pulse of the line, offline quality verification provides laboratory grade precision for complex parameters like water activity, pH, and texture profiles. These lab results serve as the foundational truth used to calibrate and validate our online sensors. We further enhance precision through advanced AI systems. Specifically, we employ convolutional neural networks to analyze high-speed camera images, rejecting cakes with irregular shapes or color non-uniformity with accuracy that manual inspection cannot sustain. To optimize this entire process, we apply the Taguchi method. By using L9 orthogonal arrays, we can evaluate 4 production factors using only 9 experimental trials instead of 81, identifying the optimal settings that make our recipes robust against environmental noise. Finally, we justify this framework through a cost of quality analysis. By investing a capex of 365,000 ringgit in advanced sensors and AI, we shift spending from failure cost to prevention and appraisal. This strategy yields around 270,000 ringgit in annual savings through improved yield and reduced scrap, resulting in a rapid payback period of just 2 years. In summary, this integrated framework harmonizes technical precision with economic sustainability to ensure Company Z thrives in the competitive export market.
Now, let's talk about the production engineering scope. My role is to design a production system that can readily meet export demand. Unlike small scale bakeries, export manufacturing prioritizes throughput, stability, repeatability, and predictable output. My focus is on how the production system is structured, balanced, and scaled to ensure consistent delivery while supporting automation and quality requirements. The cake manufacturing process is structured into standardized workstations. From a production's perspective, baking is identified as the primary bottleneck due to the fixed thermal residence time, while cooling is a secondary time constant. Standardizing each workstation allows us to control cycle times and design the system around these known limitations. To meet export volume requirements, capacity planning is centered around the oven bottleneck. The system uses multiple identical production lines operating in parallel, which increases total output while reducing operational risk. Line balancing ensures upstream and downstream processes are synchronized with oven throughput, reducing idle time and work in process. Each production line is designed as a self contained manufacturing cell, applying cellular manufacturing principles. Group technology is used to group cake variants with similar processing requirements, reducing changeovers. From a production standpoint, machinery such as tunnel ovens and cooling tunnels is selected to support continuous operation and stable cycle times rather than maximum speed. Finally, production risks such as equipment failure and demand surges are mitigated through redundancy, buffer management, and preventative maintenance. Overall, the proposed production system is robust, reliable, scalable, and aligned with export manufacturing requirements, forming a strong foundation for automation, quality assurance, and long term competitiveness.